So as the tradition goes, this is the mental break time. Okay. Now in a couple of years or something, you guys will be graduating and passing out. So this time, rather than talking about Sardarjis and Pathans and so on, we talk about you or me. Okay, so there is this engineer who has graduated and he has joined a good job, and 1 or 2 years after that he has some saving and so on, he gets married. But he is a very good engineer, he had a very high grade and so on, so he has got a very tough and demanding job. So even though he has married, he is very busy in his job and his duties are a lot. So one day the new wife, she said, you see, she complains very nicely that, you see, we are a newly married couple and so on, but you are so busy, we never take any time out and we do not relax and so on. So you also feel very sad. Oh yes, this is very true. So you said, okay, now I promise, I'll tell my company whatever happens, this weekend I will not work at all, I will be with you and we will relax and we'll enjoy and so on. So this you do on the weekend, and then you get, well dressed and this and that, then you go out into the city and you are traveling here and there and visiting and you are relaxing and enjoying, and then after some time you go to a coffee shop to relax more and to talk and enjoy. Once the coffee comes, you are still looking at the menu, and then you suddenly ask your wife, please drink your coffee quickly. She said, what? She said, please drink your coffee quickly. She said, this is so strange. For so many days we did not have any relaxation. Today we are out to relax and enjoy and take it easy. So why should I take it quickly? I will take time and relax and enjoy. He said, no. Look at the menu. Hot coffee 1 real, cold coffee 2 reals. Joke has ended. You can laugh now or later if you like. So you see, this is the stress strain diagram. You have finished the tensile test. You got a standard sample, you loaded it into the machine, you set the machine on the standard loads and so on, and you conducted the test until the piece fractured. Then you took the force readings from the machine in PSI or megapascal or kilonewton, in kilonewton, and you took the change in length extension delta L reading from the extensometer. Before starting the experiment, if you had a round sample, you measured the diameter accurately. If it was a flat sample, you measured the thickness and the width in the center region accurately using vernier calipers and so on. So you know the original cross-sectional area A0. So now in one column you have force, in the second column on your Excel you have the change in length. So F is there, delta L is there. Now you divide force by the original cross-sectional area. So each value is converted into stress, and you divide the change in length delta L by the original length, which is 2 inches here in the extensometer region, in the gauge region. So now original first 2 columns were force and displacement or extension. Now new 2 columns are stress and strain, and from these 2 columns you just select those columns and ask Excel to draw a graph, and this graph is there, right? So this stress strain graph of engineering stress versus engineering strain, because you are dividing by original area A0 and original length L0. So this is here, and now this is the basis of all the mechanical properties that we will discuss. Some we have already discussed and we told you that we will do that in more detail now. Okay, so this is the stress strain curve. If you see, then some region is the straight line region. A straight line region means until the end of this point, this is the elastic region. So at any point here, if you remove the load, it will go back to 0. If you remove from, so you have loaded until here, if you remove, it goes back to 0. Loaded until here, if you remove, it goes back to 0. But after this point, the curve becomes curve, not a straight line. Then it goes to a maximum point and then it goes down a little. So you already know that this maximum point is the maximum stress This point is the fracture point, and at this point it changes from elastic to plastic. And if you see the strain at the end of the elastic region, this is 0.02, so it is maximum 0.01, right? So it is a very, very small strain. Of course, this is a high strength aluminum alloy. If it was a lower strength aluminum alloy, there will be more strain. There will be more strain. Here it is fracturing before 0.1 strain. 0.1 means 10%. So it is fracturing before point, but other metals can go to 0.3, 0.4 strain before they fracture. So now we will start the mechanical properties from here. We will start the mechanical properties from here. The first mechanical property, and you know that you had earlier Hooke's law in your earlier mechanics. This is not Hooke's law. Hooke's law was force and deformation. You had F is directly proportional to X, so F is equal to Kx, where K was the spring constant or whatever, remember, the stiffness of the material. But now instead of force you have stress, and instead of delta L you have strain. So it is a stress strain version of Hooke's law. So calling it Hooke's law is not right. Hooke's law was F is equal to Kx. Now the law is sigma is equal to E epsilon. This is in the straight line region. If there is a straight line, there is a slope of the line. There is a slope of the line, right? In the vertical axis, remember, there is a stress. In the horizontal axis, there is a strain. So if you at any point, if you take a triangle, right, lower point, upper point, make a triangle, then the vertical side of that triangle is the stress and the horizontal side is the strain. So if you divide stress by strain, you get the slope of that line. That slope has the symbol E, and it is called the modulus of elasticity, or the elastic modulus, or the Young's modulus, named after the scientist who discovered it, right? So modulus of elasticity, elastic modulus, or Young's modulus, all the three are just the slope of the straight line region when we are doing tensile test of a metal, and the straight line region for metal means elastic region. So therefore modulus of elasticity. As an example, general steels, all steel, low strength to high strength, this modulus is about 207 gigapascal. Remember, 10 raised to 9, very high value. For aluminum and aluminum alloys, it is about 76 gigapascals. It is about 76 gigapascals. Of course, I am not asking you to memorize these values. Once you do a lot of engineering in the real field, then some of these values are permanently there in your mind, because every day if you are dealing with aluminum and steel, then some values will be permanently there. But for you, in the exams and quizzes and so on, either the value will be given or a table will be given. So you just need to understand. You just need to understand. If you were doing exams and quizzes in the class, then I will give you a few papers apart from your quiz or exam, where there are tables of properties and where there are all the equations in the course. So you don't even have to memorize or remember, right? So that is always my concern. People ask me, oh doctor, do we have to memorize? I get really upset. I can't say angry, but I get really upset, because memorization by rote, memorization, after 2 days it goes away. But if you understand it very well, and you solve one problem, two problem, three problem based on this equation, then this equation is permanently with you. But my main concern throughout the course is that, no, please don't try to memorize and reproduce something. You are to become engineers. You must understand, so that when there is a problem in the real field, you know, you forget the equation, no matter. I mean, you are in the field, in your office, you have access to any book, anything. But if you don't understand, then the book is there, but it is useless. So understanding, okay. So we will give you values, we will give you equations. Of course, once it is online, when you are doing it in your home, then the class notes and so on are already available with you. So there is not even a need to give you a formula sheet. Okay. So modulus of elasticity is the first material property that we can derive from the stress strain diagram. Okay. So this is, we are just again explaining to you that the original piece was this, the length was changed, we plotted the stress against a strain, we take any 2 points, then the stress here and the strain here, this ratio is the Young's modulus or slope of the material. Here this is outside from your book, or if you are having Callister book, it is from there. I like these type of charts, they are brilliant. If you have this page when you are in the industry working outside in the field, then it would be great. Again, you have here on the vertical axis, you have the values of E in gigapascals, right? And this column is for metals and alloys, this is for gray ceramics, this is for polymers, and this is for composites, the 4 basic material types for engineering. And then tungsten, molybdenum, steel, titanium, platinum, copper, zinc, silver, aluminum, magnesium. In ceramics, graphite, concrete, glass. In polymers, polyester, PET, PPE, HDPE, right? So this is a brilliant table. On one page, you have the Young's modulus of all the major engineering materials, and you also know that the Young's modulus of ceramics is perhaps the highest, of metals is only slightly below, but it is still very high. The Young's modulus of polymers and plastics is very low. Composites are things that we design, we make them by mixtures. So from very low to pretty high, we can moderately do it. So if this type of a chart is available with us, then we don't have to look at a lot of tables for metals separately, for ceramics separately, and so on. The second material property that we want to do from the graph is the yield strength. Some of you already know the name because of your earlier courses and so on, right? It is the borderline between the elastic and the plastic region. That is what is written, you can read it, right? The straight line region where it ends, that point is the yield point, because after that the curve will start. Or you can say where the elastic region finishes and the plastic region starts. Now, why is it called yield? I always have this in every course, that if the words are there, they have a meaning. So forget about material science. What do you think is the meaning of the word yield in normal English? You have done a full year of foundation and so on with English and so forth. Yes, one of you answered that if there is a agricultural field, then how much you produce is called the yield. So you are right, that is one meaning of yield. There is a cotton field, there is a wheat field, there is a rice field. How much you produce is called the yield. That is one. What is the other meaning of yield in normal English? Yes, you see, if I put some pressure on you, there is a political pressure. If you resist it, you do not yield. But if you cannot resist and you agree to the pressure, you yield. So to give in to the pressure is called yield. So here you see, until elastic modulus, until the end of the elastic region, the material was resisting. As soon as you remove the load, there is no deformation. But once this point is reached, the material has yielded. It has gone through a permanent deformation. Now even if you remove the load, it will not go to zero deformation. So the meaning of yielding, that you applied external pressure and now the material has permanently changed. So the meaning of yield is correct. So here in the graph, if they are showing you that if there is a very standard end of the straight line region, then we find that point. But sometimes it is very difficult, it is a smooth curve. So we cannot find where this point is. So this point is otherwise the yield point. So what do you do on the strain side? You see 0.2% strain, 0.2%, which is 0.002. So you mark this point, you make a line parallel to this, and wherever it cuts this, there you find the yield strength, and you call it 0.2% offset yield strength. So either the yield strength is very clear at the end of the straight line region, or if the curve is very smooth, then you do a 0.2% offset yield strength, and this is the end of the elastic region and the beginning of the plastic region. So one more material property.